Hello, welcome to AutoInform Diagnostic Feature. My name is Frank Massey. Over the next few issues, we're going to serialise various elements of our training courses to give an insight to both process and procedure. I hope you enjoy this feature. What I'd like to do next, perhaps, is look at some of the pure electronic components. What we've looked at so far, is mainly the hydraulic functionality, although these are both hydraulic and electronic. So remember that when you do get a fault with a system, you have to differentiate between the possibilities of a hydraulic fault or electronic control. That's one of the challenges of Common Rail. I've chosen just a few of the electronic components. Without doubt, the most critical is the rail pressure sensor. If there's one particular component that has an enormous influence over the functionality of Common Rail, it's the measurement of pressure in the accumulator. This device provides information to the PCM. The PCM then looks very carefully at what we call actual and request values. And if those values don't match, it will do something to correct it. And what it will do is drive the inlet metering valve or DRV to try and fix the problem. If it can't fix the problem very quickly, it goes into a default straight away. And that's one of the reasons why Common Rail have pressure regulation or pressure differential faults. If any of these components are for any reason out of tolerance specification, if the priming of the system isn't right, if the functionality of the high pressure pump isn't right, then this component will send a signal back to the ECU which will have the wrong value. The actual pressure in the rail is actually a voltage output from this component, and it's the voltage which we're going to interpret within the foundation module very, very carefully, very intuitively. We can measure this in several ways. We're going to introduce different methods of measuring it, but we're going to display it with the use of an oscilloscope where it's incredibly accurate and intuitive of the way in which we can interpret the pure voltage to actually predict whether the pressure generation stage, the hydraulic functionality, is working correctly. And here's the important bit: without intrusion. All of our testing is non-intrusive. We do not have to actually break into the system to get the information we need to diagnose Common Rail faults. The really crucial part of that statement is that by using that method, your diagnosis is very, very quick, very effective, in the minimum amount of time and with the minimum amount of investment in hardware and tools. The next component, and they're all important to be fair, also can cause a lot of problems and often does. This is just part of the air mass meter. This is the sensing element from the air mass meter, and it converts the intake air either as a voltage or, as is the case now, a frequency, and from that the load, the fuel requirement, can be calculated, or part of it can be calculated. The problem with these, it's environmental in most cases, that the carbon we discussed before ends up deposited on the component, causing problems. In other words, you get a deviation in the actual performance of the component against what it should actually be. So there is an environmental problem, but that's the air mass meter. We have triggers. We have camshaft and crankshaft sensors. This particular component is a camshaft sensor. It's a speed and position device. It's vital that the PCM understands the mechanical position of the engine so that the fuel timing can be established. That's done from the camshaft sensor. And fine-tuning, misfire detect, speed and position is achieved from the crankshaft sensor. Another component that's often gives rise to problems today, this is a differential pressure sensor. It measures the differential or difference in pressure pre-catalyst and DPF and post-catalyst DPF. And the purpose of this sensor is to determine if it's blocked. You've seen some of the evidence of carbon on the intake manifold I showed you earlier. This component is designed to measure where a blockage occurs in the exhaust stream, and that can have very serious consequences to the performance of the engine, and it simply uses pressure differential to generate a voltage, and that voltage is then supplied back to the ECU. Theoretically, that system should then go into a regeneration process and basically self-clean the exhaust stream or the components in the exhaust stream. And I'll come back to that. We're going to cover DPF as an introduction. We do have a standalone module for DPF and turbo diagnostics, but we are going to cover the functionality of DPF briefly at the conclusion or towards the conclusion of this training module. The last component I've chosen, as I say, this is just a few of the components. Also is very important, the APP sensor, accelerator pedal position. It's essentially a mechanical device with two potentiometers. They are movement or voltage dividers, so the actual movement of the pedal, so there is no physical link between the throttle, the driver's input signal. The driver's request is the foot on this pedal. That's the main request input. There is no physical link between this and the electronics or the mechanical systems. The functionality of this is to generate two very accurate, very distinctive signals from this component that go to the ECU. Those signals are then interpreted as a load request, and the calculation for fuel quantity then begins. So this is a very important part of the system. If this goes into a fail mode in any respect whatsoever, the system, for safety reasons, will go into a default, because quite clearly, if this were to go faulty, potentially it could cause the vehicle to drive itself. That is not possible. There is enough safety within the software parameters to prevent a faulty throttle pot from taking over control. But that is the APP sensor. Another example of where that sensor could cause a problem, if for whatever reason this component does not see 100% of load request, you will not get 100% of power or torque output from the engine. And we can look at this serially. So this is one of the things that we would examine during a dynamic test process, in other words, on the road, looking at live data. And I think that more or less covers chapter 2. What I'd like to do next, of course, very obvious thing, is look at the choice of tools. Let's look at some of the diagnostic opportunities, the tools, the hardware that we use and rely on to actually diagnose these symptoms. We're going to look at them effectively in two halves, the hydraulic tools and the electronic test tools. I hope you've enjoyed this feature, and we'll continue to follow the series throughout the various magazines. For further information on face-to-face and DVD training, visit the AutoInform website or call the phone number on the screen. I look forward to seeing you in further issues.